Let me give you a warm welcome to this lecture. I am happy that you're here, and what I'm going to do in this lecture actually is not mandatory for you to study in order to proceed further to the next lectures. In this case, this lecture will be a little bit more mathematical because I want to derive the inverse wavelet transform from the wavelet transform itself. So this will be a little bit more technical because it is not so straightforward to derive the inverse wavelet transform, but it's an occasion for me to show you something more about wavelets and in particular about the mathematics of wavelets. So I will start from the definition of the wavelet transform, and in particular first let's define the so-called function psi, which is the mother wavelet. This is the so-called mother wavelet, and it is a function in general of time. It depends on more than one parameter. Actually, it depends on two parameters that we will call b and a. So t is the parameter actually related to time, so it's the independent variable related to time, and then we have other two parameters. B, let's say, it takes into account a translation in time, whereas a is related to the inverse of a frequency. Then if we multiply this by 1 over square root of a, we define this as a set of wavelets. So psi ab of t, these are a set of functions that define the wavelets, starting from the mother wavelet. So the wavelet transform is defined starting from this set of wavelets here, which in turn are defined in terms of the mother wavelet. But the wavelet transform is defined like this. So we have W written in terms of the function psi, so the wavelets. So these are a set of functions. So we write the subscript psi, and then this wavelet transform is applied to the function f, and it will depend on two parameters a and b. This is defined, so this triangle here simply means that I'm going to define the wavelet transform like this. It's an integral from minus infinity to plus infinity of the function f of tau. So this is a function, the function f, to which we apply the wavelet transform, and we call it f. It will be a function of tau, and then we have psi bar, which is the complex conjugate of psi ab. So we have psi bar ab of tau d tau. This is the starting point that we consider in this lecture. What we are going to do is we are going to derive the inverse wavelet transform. So in particular, we will have something like f of t, or tau if you want, and this will have to be defined as some kind of integral of the wavelet transform and blah blah blah. So we have to find the inverse transform. That's our objective for this video, for this lecture. So what I'm going to do is I'm going to take the wavelet transform, W psi of f, which depends on a and b, and I'm going to multiply it by psi ab of t, and I will also multiply this by 1 over a squared, and we will see that this factor 1 over a squared appears in the inverse transform. Then we are going to integrate over a and over b, and the integration is performed over the real axis for a and also for b. So from minus infinity to plus infinity. Now let me substitute this expression here for w psi here. And then I'm also going to use this formula in here and also in here. And of course, in that case, I have to take the complex conjugate. So let me do that. Here, this double integral will become a triple integral because I'm substituting another integration which is performed over tau. So here I have integral from minus infinity to plus infinity, integral from minus infinity to plus infinity, integral from minus infinity to plus infinity, and then I have f of tau 1 over a cubed, and I have a cubed because I have a factor which appears here and here. In particular, I have 1 over square root of a, but I have 1 over square root of a here and here, so that will become 1 over a, and then I multiply it by 1 over a squared, and that's of course 1 over a cubed. And then I have psi of t minus b over a, and this simply comes from here. But I also have psi bar of tau minus b over a, and that comes from the definition of the wavelet transform. And then I have to integrate over a, over b, and over tau. So I can swap the order of integration because all these integrals are performed from minus infinity to plus infinity. So the order doesn't matter in this case. Now I need to do some more steps, actually. And what I'm going to do is I'm going to substitute in place of psi here and psi bar the definition in terms of the inverse Fourier transform. So in particular, for example, I can write psi of t minus b over a like this. So psi of t minus b over a can be written like this. It's an integral from minus infinity to plus infinity of psi hat, which is the Fourier transform psi of omega 1, and then I have e to the I omega 1 t minus b over a, which is the argument that appears here, and then I have d omega 1 over 2 pi, like this. And I will do, of course, something similar for psi bar, and instead of t, I have tau, but nothing major changes. And then I can rewrite this as not just the triple integral, but I have 5 integrals to carry out actually. So don't be scared too much because we will see that after all it will simplify. So in this case, let me just write one integration symbol because otherwise it's going to become too cluttered, too nasty. If I write 5 integral symbols, that's way too much. So let me just write one integration symbol, but I mean, it's just a shorthand. And then I have f of tau, I have 1 over a cubed, I have psi hat of omega 1, e to the I omega 1 t minus b over a, and then I have psi hat bar, which comes from here, and in particular when we replace the inverse Fourier transform here. So I have psi bar hat, sorry, psi hat bar, actually I should say psi hat bar, and then this will depend on omega 2. I have to be careful here because I have to change omega 1 to omega 2 because these are dummy variables because we are integrating over these variables. So I cannot call them the same way. I have to change the name. I have to label them differently. And then I have e to the minus. In this case, I have a minus because I have to take the complex conjugate of this, of the complex exponential. So I have e to the minus I omega 2 tau minus b over a. And then I have some differentials. I have d tau, and I have a factor of 2 pi squared in the denominator because it comes from the inverse Fourier transform, and I have 2 inverse Fourier transforms, so I have a factor of 2 pi squared here, and I have dA d omega 1 d omega 2 dB. So we are almost done with all these integrals, but actually we have to make one more effort. And unfortunately, that effort consists in replacing another integral instead of one of these functions. And in particular, we have to replace the inverse transform here for the function f of tau as well. So what I'm going to replace instead of f of tau is this. F of tau can also be written as integral from minus infinity to plus infinity f hat of omega 3 e to the I omega 3 tau d omega 3 over 2 pi. So this seems very complicated, and actually I can agree with you if you think that, because it's quite nasty, quite complicated. It seems more complicated than before. But this is more convenient because we will see that in this case the integration over these complex exponentials will simplify. So it will give rise to Dirac delta functions or Dirac deltas. They are not really functions, but I will tell you a little bit more about it. And I want to convey the ideas, okay, the main ideas. I don't want to give you the complete mathematical details all the time because otherwise we will not, of course, be able to explain everything in detail. So this is my way of tackling uh, these explanations. I'm trying to give you my insights. It's not so, let's say, straightforward to find explanations regarding all the mathematical steps to find the inverse wavelet transform. Anyway, let's move on. What we need to do is we need to replace this integral here as well. So basically we have actually 6 integrals to carry out if you think about it, because we have the integral over tau, the integral over a, over omega 1, over omega 2, over omega 3, and over b. So we have 6 integrations actually. That's why it's complicated. And at the end, we will see that we can reduce all these integrations to just 2 integrations, because we can carry out some of these integrations without, let's say, much of an effort. So let me put an equal sign here. So this will be equal to, but before writing this expression below, and we will write the expression here. But before doing that, I will carry out one integration. And in particular, it is convenient to rewrite the expression. Well, let's write the expression here. So let me do all the steps without skipping anything relevant. So I have an integral sign which actually embodies 6 integrations that we have to carry out, because remember that we have 6 integrals to carry out, and that's fine. And then I have a bunch of complex exponentials that I can rearrange. So let me put the complex exponentials in here. I have e to the I omega 3 tau, which comes from here. And then I have e to the I omega 1 t minus b over a. And then I have e to the minus I omega 2 tau minus b over a. I also have to divide by a cubed, and let's put a cubed here. If you recall, we have a cubed in the denominator, and that's exactly here. And then what else do I have? I have a factor of 2 pi cubed. So in this case, it's 2 pi squared, but remember that we have another factor of 2 pi here. So I have to remember that I have to put 2 pi cubed. So here I have d omega 1 over 2 pi cubed. So remember that also the order of these differentials doesn't matter. So I have d omega 1, d omega 2, d omega 3, and then I have d tau, I have dA, I have dB, and here I have left some space because I have f hat of omega 3, I have psi hat of omega 1, and I have psi hat bar of omega 2. So you see we have 6 integrations. And now we are going to carry out the integration over tau. It will be simple because you can see that actually we don't have to integrate over these functions. When we integrate over tau, we only have to integrate over this complex exponential multiplied by this complex exponential. So the integral that we have to carry out is the following. So let's only consider the integration over tau, right? We have e to the I omega 3 minus omega 2 over a, and then I have tau d tau, and this also gets multiplied, so I'm considering this exponential multiplied by this, and then in this case I can also factor out a complex exponential of this kind, e to the I omega 2 b over a. So it comes from here, from this part of the exponential, because this complex exponential can be written as a product of e to the minus I omega 2 tau over a multiplied by e to the I omega 2 b over a, like this. So if we integrate over tau, maybe I should say when we integrate over tau, this can be factored out of the integration over tau. So the integration can be performed only over this complex exponential, if you think about it. And it's not complicated, because when we have an integral of this kind, so the integral of course is performed from minus infinity to plus infinity. But when we have an integral of this kind, so the integral of e to the I alpha tau d tau, this will give rise to the Dirac delta of alpha multiplied by 2 pi. So this is what we get. And now in this lecture I will not explain some detail regarding the Dirac delta or where this result comes from. Not in this lecture. So we take this for granted, and this means that I can rewrite this as 2 pi delta of omega 3 minus omega 2 over a, and then I have e to the I omega 2 b over a. Okay? Let me also mention something that has now come to my mind, and in particular you can think about it, because when we integrate, for example, over a, here you can see that we have a in the denominator, right? So there might be some kind of discontinuity when we carry out this integration. So we should take that with a pinch of salt. But let's not care too much about it. Let's not care too much about the convergence of these integrals. In this case, I just want to give you the main ideas, and let's try to hide these mathematical details under the rug. So this is the first integration that we can do, and this will become equal to, so this will be equal to, we have integral, here we have e to the I omega 1 t minus b over a, which is exactly this part. Then I have 2 pi delta of omega 3 minus omega 2a over a, e to the I omega 2 over times b over a, and then I have f hat of omega 3, I have psi hat of omega 1, psi hat bar of omega 2, and then I have 1 over 2 pi cubed a cubed. I have d omega 1, d omega 2, d omega 3, dA, dB. So in this case I have only 5 integrals. Well, only, let's say, quote unquote only, but let's say, we improved, because we started from 6 integrals, and that now we are at 5 integrals, and we have a Dirac delta. here, Dirac delta of omega 3 minus omega 2 over a. And when this function, well, actually I should not call it a function, but for simplicity I might call it function because actually it's a distribution, but let's call it function if necessary. When this multiplies f hat of omega 3, there is a property of the Dirac delta that I can use. So I have delta of omega 3 minus omega 2 over a times psi hat of omega 3. This is also equal to delta of omega 3 minus omega 2 over a times f hat of omega 2 over a. So I'm using a simple property of the Dirac delta, and in particular I can always evaluate a function which multiplies the Dirac delta at the point at which the Dirac delta is located. So this is what this equation tells me. And basically that's what I'm going to do. I'm going to replace f hat of omega 3 with f hat of omega 2 over a due to the property of the Dirac delta. Simple as that. And then I can integrate over omega 3 because now I don't have omega 3 elsewhere. I only have omega 3 here in the Dirac delta. And when I integrate the Dirac delta over the real line, because I have to integrate from minus infinity to plus infinity, I will get 1. So what I can do is this. I can set this equal to integral, and I have e to the I omega 1 t minus b over a. I have a factor of 2 pi here. I have, instead of the Dirac delta, I have just 1. And then I have e to the I omega 2b over a, f hat of omega 2 over a, psi hat of omega 1, psi bar, or actually I should write it like this, psi hat bar of omega 2. Then I divide this by 2 pi cubed, a cubed, and then I have d omega 1, d omega 2, dA, dB, because I have integrated over omega 3. So I am left with only 4 integrals. Now, the next step is to do something similar for the remaining complex exponentials. I have integral of e to the I omega 2 minus omega 1 b over a. So this can be integrated over b. And I have e to the I omega 1 t over a. So basically, I can rewrite this complex exponential as a product of this exponential here and e to the minus I omega 1 b over a, which is here. It has been factored here. It has been written inside this single complex exponential, which takes into account also this complex exponential here. So we have e to the I omega 2 b over a times e to the I omega 1 over a times minus b. And this can be put together, these two can be put together into this complex exponential here. And then, of course, everything multiplies this complex exponential. And I can integrate this over b, because all the other functions here do not depend on b. So I can do this integration without taking into account other functions as the integrand for this integral here. But this integral will give you 2 pi, so let me do it a little bit slowly. We have to integrate over b, and if I put here a denominator inside the differential for the integral, I should multiply by a, And now you can see that when I integrate this from minus infinity to plus infinity, I will get, of course, a times 2 pi delta of omega 2 minus omega 1, because it's actually the same integral that we had before, which gave rise to the Dirac delta. And then I have to multiply this by e to the I omega 1 over a times t. So this quadruple integral will become a triple integral because I carried out this integration over b. So I can write integral of 2 pi coming from here, but I have another factor of 2 pi coming from here, so I can write 2 pi squared. Then I have a times delta of omega 2 minus omega 1 e to the I omega 1 over a times t, f hat of omega 2 over a psi hat of omega 1. Then I have psi hat bar of omega 2. I divide by 2 pi cubed a cubed. Then I have d omega 1 d omega 2, and then I have dA, because I have integrating over b. I have integrated over b. Then now I can integrate over omega 2 actually. So here you can see that I have the Dirac delta. This does not depend on omega 2. This one here depends on omega 2, and this one here depends on omega 2. But since this Dirac delta multiplies these functions, I can replace omega 2 here with omega 1, because you can see that this Dirac delta is located at omega 2 equal to omega 1. So here I can put omega 1, and also here I can put omega 1. So when I integrate over omega 2, the integral will give rise to 1 when I integrate over this delta. So let me just cancel this omega 2 this delta of omega 2 minus omega 1. So I have 2 pi squared here. I have integral, so let me cancel this. Since I have integrated over omega 2, I will have to get rid of this d omega 2 as well. So I have d omega 1 times dA. And now you can check that here I have psi hat times psi hat bar. But this will give rise to psi hat of omega 1 mod squared. I have to take the mod squared, right? Because I have the function multiplied by its complex conjugate. So I can rewrite this in this manner. I have this integration, which is actually a double integration in this case, because I have two differentials here. And this 2 pi squared here will cancel some factors here. 2 pi cubed I have there, so I can simplify the expression a little bit. I have a here, which multiplies a cubed, so I can simplify this a little bit. I have e to the I omega 1 t over a, f hat of omega 1 over a, and then I have mod psi hat of omega 1 squared, and then I divide this by 2 pi a squared d omega 1 dA. Now we are almost there. We are not done yet, because in this case this is a double integral that you cannot really separate if we write it like this. So here I have a double integral. Remember that I have to integrate from minus infinity to plus infinity, from minus infinity to plus infinity here, so over omega 1 and over a. But the integrand that I have here depends both on a and on omega 1. And I can show you that we can rewrite this integral by means of a product of two integrals. one integral will be performed on one variable and the other one will be performed on another variable. And this will simplify the expression a little bit, and we will be able to find the inverse wavelet transform, which is not really apparent from here. What we need to do is we need to change the variables. We need to make a change of variables of this double integral. In particular, let's write down a variable lambda equal to omega 1 over a, and another variable s equal to omega 1. So we are changing variables. We are going from the set of variables omega 1a to the set of variables lambda s. And in order to make this change of variables, we also need to calculate the Jacobian of the transformation, because it will appear in the double integral when we make this change. So we need to write the Jacobian of the transformation, and in particular, we need to write the lambda s with respect to omega 1a. So this will be the Jacobian matrix, and I can rewrite it like this. In particular, when I write the expression like this, in the first entry of the matrix here, the first row, first column entry will be the derivative of lambda with respect to omega 1. So this will simply give 1 over a. Then here I will put the derivative of lambda with respect to the second variable here, which is a. So we have minus omega 1 over a squared, which is the derivative of this expression with respect to a. Then we have the derivative of s here with respect to omega 1, and I have to put it here in the second row, first column, and that will simply give me 1. And then I have the derivative of s with respect to a, and I have to put it here, but I have 0. So this will give me omega 1 over a squared, like this. And then I have to substitute these variables here, and in particular, from these conditions, I also find that omega 1 is of course equal to s, and a is equal to omega 1 over lambda, which is equal to s over lambda. So inside this expression, I have to replace omega 1 with s and a with s over lambda. So let me rewrite this double integral here. So I have to carry out a double integral as well, and it's quite easy to see that the integration will have to be performed from minus infinity to plus infinity here as well, because the variables omega 1 and a, well, they range from minus infinity to plus infinity. So s will also range from minus infinity to plus infinity, and if a is not equal to 0, then lambda is well defined. As I said, let's not get into the technicalities with discontinuities and so on and so forth, but you can easily understand that also lambda will range from minus infinity to plus infinity, right? Because both of these variables here range from minus infinity to plus infinity. So the double integration is still performed from minus infinity to plus infinity for both variables. And here I have e to the I, omega 1 over a is equal to lambda times t. T remains equal to t, because we didn't change that. Then I have f hat of omega 1 over a, but omega 1 over a is just lambda. F of lambda. Then what do I have? I have mod psi hat omega 1 is equal to s. So we have psi hat of s squared. We divide by 2 pi a squared, but instead of a, I have to write s over lambda. So I have s squared over lambda squared. And then remember that I have to put the Jacobian, omega 1 over a squared, but remember that instead of omega 1, we have to write s. So this is equal to s over a squared, but a squared is equal to s over lambda squared. So we have s over lambda squared. So this is equal to lambda squared over s. This is the Jacobian of the transformation. And we have to be careful though, because, well, in this case here, we have d lambda s over d omega 1a. But we have to be careful because in this case here, inside this double integral here, what we will have is the Jacobian of omega 1a with respect to s lambda here. So in particular, in this case, we will have the determinant, which is the Jacobian, or I mean, it's the determinant of the Jacobian matrix, which is called the Jacobian. Okay, so in this case here, I'm considering the determinant of the Jacobian matrix. And in particular, let me write it like this. So I have to take the determinant here, and I will indicate it with these straight bars, and the determinant of this matrix as well. So in this case, the notation is more consistent because it was not so consistent before. I mean, a matrix is not equal to a scalar, but the determinant of the matrix will be equal to the scalar here. And from multivariable calculus, if we want to consider the Jacobian of omega 1a with respect to lambda s, or s lambda actually, because the determinant of this matrix will be equal to the determinant of the transpose, which is equal to this determinant here. So if I swap the order between s and lambda, I will get the same result. And you can check that this is equal to 1 over the determinant that we have here. So d lambda s d omega 1a. And I write it in terms of the lambda and s variables. So I have s over lambda squared. So in this case, inside our integral here, we have to put s over lambda squared. So let me cancel this. And I simply write s over lambda squared, and then I integrate over lambda and over s. I can cancel this s squared with s, and also lambda squared with lambda squared here. And you can see that these two integrals actually can factor, because we have integral from minus infinity to plus infinity of mod psi hat of s squared over s ds, which multiplies the integral from minus infinity to plus infinity of e to the I lambda t f hat of lambda d lambda over 2 pi. But now you can check easily that this is equal to the inverse transform. So this will be equal to f of t of this variable here. F will be the inverse transform, of course, the Fourier transform. And then we find f of t multiplied by this integral, which means that this product here, this function multiplied by this integral, which is just a scalar, and that's equal to the starting point. And the starting point was this integral here. So we found that this integral here can be written as integral from minus infinity to plus infinity of mod psi hat of s squared over s ds times f of t. So if we divide by this integral, we find f of t written in terms of the wavelet transform. So you can see that we have this somewhat complicated double integral. We have to integrate over a and over b. Okay, so we are spanning all these functions psi sub ab. We are changing a, we are changing b. So it means that we are changing the frequency of these wavelets and also the translation of those wavelets. And we are multiplying those wavelets by the wavelet transform. We are carrying out this integral. Then we have to divide by this integral in order to find the function f of t. So you can see that this kind of theory, mathematical theory, is more complicated than the Fourier theory. So where you have Fourier transforms, Fourier series, and I just wanted to show you some mathematical details, because if you are interested, then why not show you these details, which are more advanced, because I mean this is not necessary in order for you to understand the details of the course. But I think actually that this might be helpful to you if you want to dig deeper and understand the concepts more thoroughly.